There is something out at sea, terrorizing the world shipping. This is the story of a wave that is sinking ships around the world. A killer that defies all scientific understanding, and that no ship is designed to withstand. It is one of the best-kept secrets of the sea that once a week a ship sinks to the bottom of the ocean, often without mayday or any clue as to what happened. Freak waves are practically impossible. Scientists have understood ocean waves for centuries. They are simply made by the wind. The stronger the wind and the longer it blows, the bigger the waves. In order to predict the biggest wave a ship will meet, scientists use a set of mathematical equations called the linear model. This says that in any sea condition, there is a limit to how big the largest wave will be, and that mariners' tales of monster waves that come out of nowhere have got to be wrong.
Mariners are like fishermen, aren't they? I mean, they come back from the sea and they tell all kinds of interesting stories, and people look at them suspiciously.
It's sort of like, you know, the fish that got away, and he says, oh, that was 10 meters long, you know. Well, waves are sort of the same.
Jim Gunson of the Met Office uses the linear model to explain why freak waves shouldn't exist.
Using the linear model for a given sea state, this bell-shaped graph gives the probability of a certain wave height. And it's like in a population of children in a class. There is an average height of children, and most children are around that height. Some are quite a bit taller or shorter. There's the chance that a child is 3 or 4 times the height of the average child is very, very small.
So, according to the linear model, even in a fierce storm where average wave height may be 12 meters, the chance of meeting a 30-meter wall of water is practically zero.
Using the linear model for a 12-meter sea state, the chance of finding a 30-meter trough-to-crest wave height is 10 to the minus 5, which is 0.00001. To put it in perspective, a wave like that would come along using the linear model once every 10,000 years.
The linear model is so well accepted that the entire multi-billion-pound shipping industry relies on it. Meteorologists use it to predict wave height, and naval architects to calculate ship strength. And the biggest wave used in ship design is just 15 meters. The idea that there might be freak waves out there seemed impossible. Instead, any mysterious disappearances at sea have been blamed on far likelier culprits, like corrosion and human error. But then one day, something happened that forced scientists to look again at their ideas about ocean waves. On New Year's Day 1995, a storm was brewing in the North Sea. The Draupner oil rig was 100 miles out in the harshest of weather. The sensors were regularly reading waves of 12 meters. When suddenly, out of the blue, came a wave that was so high and so steep, scientists had thought it was impossible.
me, it changed everything. Really changed everything. This wave is at 26 meters. It's so much bigger than the background sea state.
When the New Year's Day wave came along, which fits this picture, a 30-metre crest-to-trough height in a 12-metre sea state, alarm bells started going off because of the very low probability of this wave, yet we saw it.
The sensors measured a wave so steep and so high it should only occur once in every 10,000 years. The New Year wave shocked wave experts. Among them, Julian Wolfram. He has spent years since then studying the same part of the North Sea, looking for more freak waves.
What we need to do is to study waves like this, because we need to know how frequently they occur, because if they occur quite frequently, they could actually pose a serious danger to offshore structures and ships.
Wolfram was looking for any waves that were bigger than the linear model would predict. And to measure them, he installed a radar device, looking down to the sea surface.
We have a device which faces down to the surface of the sea and basically sends out an electric pulse, hits the surface of the water and comes back again. And we time the amount of time it takes to go down and come back. And from that we can estimate the distance from the radar to the wave. And we do that continuously, so we actually get the profile of the surface.
Over 4 years, Wolfram measured every large wave that hit the platform. And when he plotted the size of these waves compared to the height of the waves around them, he found something completely unexpected. The linear model predicts that when you plot the height of individual waves relative to the waves either side, they should all lie on a straight line. And when the average size of the waves was small, the linear model held true. But he found 24 waves that veered well above the line. These biggest waves occurred far more frequently than the linear model predicted. It appeared that these 24 waves were a completely different sort of beast.
Well, one of the things we learned when we plotted out the graph was that in fact the really extreme waves are different from the slightly smaller waves. They have different characteristics. They tend to be significantly steeper. They also tend to be higher than we would normally expect based on the ordinary theories we've used up to date. They are unusual. They are freak waves.
It seemed Wolfram really had found the rogue wave of Mariner's myth. For the shipping industry, Wolfram's research could have been a disaster. If there really were freak waves out there, then potentially billions of dollars were at risk. It could mean having to redesign every single ship. According to traditional theory, such waves should be incredibly rare. Yet here were two, within days of each other. So what was going on? Science mobilized every technology to solve the mystery. Using a new radar satellite, Susanne Lehner of the German Aerospace Center began searching for freak waves around the globe.
Now, with these radar images, you can really see the individual waves. You can see wavelengths, wave directions, wave grouping.
The European remote sensing satellite travels across the ocean using highly sensitive radar to get a detailed picture of the sea surface. It can pick out individual rogue waves from anywhere in the world.
What we get is an image like this one. This is actually the radar image with the highest wave we found on all of our 30,000 images we analyzed. This is a 30-meter wave here, the high crest followed by a very low trough.
This is exactly the size of wave which hit the Bremen and the Caledonian Star. The sort of wave that science said was practically impossible. And in just 3 weeks' worth of data, they found over 10 such huge waves out in the deep ocean.
What you can see here is this highest wave we found of about 30 meters, that is color-coded in red. The next highest waves here are about 27-meter high waves, color-coded in orange. We find another high wave here in the North Pacific. This is again a kind of 26-meter high wave here. We did not expect to find in this limited amount of time so many of these extreme wave events.
If the satellite data is right, it looks as if freak waves occur in the deep ocean far more frequently than the traditional linear model would predict. The question is, why? The answer seems to lie in a completely different branch of science. Al Osborne inhabits a strange mathematical world where almost anything can happen. It's the bizarre non-linear world of quantum physics. In this world, objects appear and disappear according to one remarkable equation, the Schrödinger equation.
The Schrödinger equation, quantum mechanics. We have TV programs called Quantum Leap and so on and so forth. So we all think we know something about that equation. There's a version, however, modified, that describes deep water waves.
Osborne is one of the world's leading wave mathematicians. For 30 years, he has been obsessed with the theoretical waves described by the Schrödinger equation. The equation describes a theoretical water surface where huge waves can suddenly leap up out of nowhere, where for some reason normal waves become unstable and grow huge.
The physics of the nonlinear Schrödinger equation we can see in this simple example. In the beginning, it doesn't seem like there's anything happening, and we could all just give up and go drink a beer if we wanted. On the other hand, we could keep moving forward and maybe something will happen. What we'll see is this central wave here is going to start to grow. It's growing because it's robbing energy from its two nearest neighbors. So here it's starting to come up. You see it's growing. It's stealing energy from the nearest neighbors. And these waves are starting to drop. See how this is coming down here? Look at that decrease. And now, in its full glory, it's a very large wave. It has two smaller waves on each side and two rather deep holes in the sea around the peak.
In Osborne's theoretical world, these non-linear waves could grow into monsters. But the idea of waves becoming unstable like this in the real world was so outlandish that oceanographers said it could never happen.
If you talk to people who know something about ocean waves, nobody was going to take this theory seriously.
Until someone sent him the profile of a wave. It was the one that hit the Draupner oil rig in 1995. The New Year wave.
changed everything. Really changed everything.
The New Year wave looked identical to one of his theoretical, non-linear waves.
I was flabbergasted. Absolutely flabbergasted. It just looked exactly like one of these exotic solutions to the nonlinear Schrodinger equation. One of the ones that we threw away over the last 30 years because we said, this kind of thing can't happen. This kind of thing is just too strange. Yet, it just sits there and it looks at you, and you have to entertain the possibility that it is a real effect. And it might really have something to do with these extreme waves in the ocean.
If Osborne is right, here is the reason why rogue waves occur in the deep ocean. It isn't to do with strange local conditions. It's because waves start to behave in a bizarre, non-linear fashion. For some reason, they become unstable and start sucking up energy from waves around them.
You have what's called a rogue sea. Now, mariners have known about this. You look at the sea state in one moment. Everything just looks random, boring waves that we've known about for a long time. But then, one of these waves will come up. They're all there. They're all hiding away. One of them will come up. Then a little later, another will come up. But in between, you won't see them necessarily.
Osborne's theory means that there are two types of wave: the ordinary stable linear wave and an unstable non-linear monster. A wave that at any point can turn into a rogue.
It says that there are really two kinds of waves. Amazing thing. Not the old boring sine waves that we've known about for 2 centuries. Not only those, but there's another kind of wave. It's a really special beast. It hides below the background waves and then comes up every once in a while.
This could then explain what Wolfram saw in the North Sea. And it could explain what caused the large number of waves observed by satellite. It seems that there is a separate population of waves out in the ocean that are higher and more frequent than anyone had thought possible. And there's something that makes these waves especially deadly. It's not just their size, it's their shape. The linear model used by the shipping industry has always assumed that waves are smooth and gently sloping. So ships are only designed to cope with undulating waves like these. But according to mariners, freak waves are very different.
It was a vertical wall. It wasn't a sloping wave. It was a vertical wall of solid grey water.
I likened it to the White Cliffs of Dover. It just looked as though there was this enormous great cliff ahead of us.
Freak waves aren't the smooth, undulating waves ships are designed for. They are so steep, they can actually break. It means they can hit a ship with astonishing force.
The reason why rogue waves are so damaging is because they're breaking. It's no longer really a wave. It's just a pile of water coming flying at you, and it just goes bang.
Engineer Rod Rainey analyzes ship damage for the marine industry. He has been calculating the huge forces that these giant breaking waves have on ships compared to normal waves.
This ball here represents the force of a 3-meter classical linear wave hitting a ship. That's the force of about 1.5 tons a square meter. This represents a typical storm wave, say 12 meters high, hitting a ship. About 6 tons a square meter. And this represents a force from a rogue wave. That's about 100 tons a square meter.
This force is far greater than most ships are designed to withstand.
We've looked very carefully at ships that have been damaged by breaking waves, and we are sure that the pressures that you can get over substantial areas are about 100 tons a square meter. Now, that compares with what a ship is normally designed for, high up on the side, which is typically about 15. Now, just to be clear here, that 15 tons per square meter is what it can take without any damage at all. It can take perhaps double that if you allow it to dent, but it can't take 100 tons a square meter. That will hold it.
It seems that rogue waves are not only out there, but they are far more powerful than any ship can handle. All the scientific evidence suggests that the old explanation for why the shipping industry loses a ship a week may be inadequate. It may not be just corrosion or pilot error. Some, at least, must be due to freak waves. It means that at last we can lay to rest some of those mysterious disappearances at sea.